Hello and welcome to another video. In this video we're going to be doing an intro to binary search, and I'm going to give you a template you can use to solve all binary search problems. That is very easy and is going to make you have like the least amount of mistakes possible. Because let's get into it. So first of all, like, what is binary search? When do we need to use it? So let's answer the first question. It's like, when is it applicable before we can talk about what it is? So the time binary search is applicable is basically if you can answer a question. So if you can check some value in an array and from there eliminate half the values. And so what I mean there is if we have some array and we just randomly pick a value like this value, and that value is going to tell us, like, we're looking for some result. And based on what value we have, we can either eliminate this side from the search or this side from the search. And so if the array has like random numbers, let's say we're looking for a number in an unsorted array or something, and the numbers are all over the place, like 9, 8, 2, 10, 50, and so on. Like if getting a number doesn't tell us anything, then we can't do binary search. So that's basically when we can use it, is we can check some value in an array, and from there we can eliminate half the values. And then how does it work? So it works pretty simple way. We have two bounds. So we have a left and a right bound. And we just always pick the center. Then by looking at the center, we usually have one of three conditions. We found what we were looking for, in which case we can return. Or I guess one of two conditions, or we eliminate one half of the search. And we keep doing this until we find what we're looking for. Or not, and we just exhaust the search. So what's that going to look like? So let's show that for like a really basic example. So let's say we have a bunch of numbers in the array, and the number is just the index. So at index 0, we have 0. At index 1, we have 1, 2, 3, and so on. But we don't know that. We just know the array is increasing. And let's say we're looking for the number like 1. So what would happen is you're going to have these two bounds, and you're always going to pick the middle. And if there's like a two middles, you just pick the leftmost one. So in this case, we would pick this as our middle. And so we're looking for 1, right? So our target value is 1. We say like, okay, well, what does this value tell us? So this value is not 1. We didn't find what we're looking for, but what side can we eliminate? Like, we know this is too big and we know this is sorted. So we know we can eliminate this section. So then what we do is we just say, okay, well, we'll just actually eliminate that section from our search. And then our right bound will now be over here because we checked all of this. Then once again, we'll pick a middle value. So in this case, it'll be this because there's 2. And we say, oh, this is what we found. So we just returned here. And so that's one example. Another example that's pretty common is you'll get like the leftmost or rightmost value greater than x or less than x, and so on, right? So let's just show in a quick example. Let's say we have the sorted array again. So we have some values. Now let's say our values are just going to be kind of simple again, like this. All right, so we can't get an exact match, but we can like find something. Okay. So what does this look like? So we're trying to find leftmost, let's say, value greater than whatever, 9. So how do we do this? So the answer should be 10, right? Leftmost value greater than 9. So how do we do this? Once again, we'll pick the middle. So we'll pick this 20 and we'll say, okay, is this 20 greater than 9? It is greater than 9. So what I like to do is I like to make a result variable personally, and I'll just store this index. And so 20 might be our answer. Like, or let's do leftmost value, I guess. So we'll store the 20. The 20 might be our answer, but we don't know for sure because we don't know what numbers are in this array. But this does allow us to eliminate a bunch of stuff, right? So because 20 is greater than 9, we don't have to check all these because we're looking for the leftmost. And similarly, if the value is smaller, we would just go the other way. So here we can eliminate all of this. So let's do that. So we're going to eliminate all of this. Now we just have this space. So let's check again. So the leftmost, or the middle here is going to be this. So we say like, okay, is this greater than 9? No. Well, if it's not greater than 9, we know none of this is either. So we can get rid of all that. Now we only have these two. And then we're going to pick this, because if there's 2, we'll pick the left. So this is greater than 9. This is 10. So we'll store that in the result. And then we're going to move this up here. And then we have one last value check, 15. Actually, sorry. We're not going to move this up here because we're looking for values to the left of it. So when we're looking for values to the left of it, there is nothing to the left. So then we're done. And then we'll just return 10. So those are the kind of questions you're going to be asked, is like, this is pretty common, and we'll go through some of those examples, and just find a target. So the only difference between this and find a target is for the target you just return right away, where here you need to actually go through everything. Okay, so what is like the pseudocode and template and stuff I like to do? So if we're looking for a value, then in either case, we're gonna make a left and a right bound, and there'll be some value, you know, like x, y. Usually it's gonna be like 0 and the end of the array. And then you have a while loop. So you want to check all values between them. And then you get a mid value or a pivot value. And the mid and the pivot is just going to be the middle of those. So in Python, you can do this. In other languages, this might cause overflow. So the better way of doing this is left plus right minus left over 2. This will never overflow. So this will give you this value. And then based on this pivot value, we're gonna check it, we're gonna do some stuff, and we're either gonna move the left and the right pointer. So if we want to shrink our window to the left, we're gonna say right equals pivot minus 1. And if we want to shrink our window to the right, then we'll do left equals pivot plus 1. And then we'll store some stuff in a result or whatever if we need it. So usually I have a result here. And then if my pivot value matches my condition, I modify my result, and then I like return it. So we're going to use this all throughout in all these problems. And that's the basic idea. So you can go from, if you have this predictable array, right? Like once you get a value, you can eliminate half. You can go from linear to log. And so there's kind of like different things you can check, but usually it's going to be predictable array is one condition to use binary search. Sorted or kind of sorted or whatever. And the other condition is actually harder to think of, but it's when the thing you're trying to maximize or minimize, max or min, is also predictable. So a common example of this is like find shortest time where some task can be complete. So we know that like if a time can be completed at time t, or earliest, I guess, right? Earliest. We know that if a task can be completed at time t, then we know for sure it will be completed at time plus 1, time plus 2, time plus 3, and so on. And if it can't be completed at time t, then we know for sure it can't be completed at any time before. So we can kind of do the same thing with the binary search. Let's say our time is like 1 to a million or whatever it is. We'll pick some random time and we'll say like, oh, for this one, can this be completed? We'll just write a function like, can a task be completed at this time? And if it can, then we will get rid of everything bigger. And if it can't, then we'll get rid of everything smaller. And so we can actually binary search on the result we're trying to get. So that's the other like not so obvious binary search use case, and we'll look into both. Okay, so let's start with the simplest. So literally we have a sorted array. We're trying to get a target. So here, pretty easy. So we'll just do 0 length nums minus 1. And like I said, we have 3 cases, bigger, longer, or bigger, smaller, or we hit the target. So while left is less than or equal to right. Like I said, in Python you can do this. In another language, use the other format I suggested. So basically we just check like if nums p equals target, return the index, which is p. If nums p is less than the target, that means we need to check the right side. So we're going to move our left pointer. It might be kind of unintuitive, but like if a left is over here and a right is over here, and I need to go to this right side, I need to move this left over here. So by moving the left, I'm moving the window to the right. By moving the right, I'm moving the window to the left. Okay, so we checked everything up to P, so we just need to go past that. And then the other case is the other way. And then if we were checked everything, we can just return false or whatever, -1 or something. Okay, let's give that a go. Oh, wrong right away. Perfect. Okay, let's see. What do we do wrong this time? If nums p is greater, oh right, so if nums p is greater, it's on the right, so we need to go left. So to go left, we actually need to go this way, right? Got it reversed. Usually when you get these wrong, it's because you have these things backwards, so that's like the first place you want to check. Okay. Okay, moving on to the next. So this is kind of similar. So we're guessing a number higher or lower. We can guess 1 to n. So left or right will be 1 to n. And basically when we guess, it tells us which way to go. So based on the guess, if we have it correct, we'll return. If it tells us less, then we'll go up. If it tells us more, we'll go down. So same kind of thing. Here we know for sure we're going to guess the number correctly eventually. So result equals guess of the pivot. If result equals 0, we just return the number. If result is -1, then we guessed higher. So if we guessed higher, we need to go left. So this way. Otherwise, this way. So yeah, this is what I would recommend for, like, if you know you're returning, just have a check for, did I get it? Otherwise, go one way or the other. Hopefully you get it right this time. Okay. All right, next. Okay, so this one's going to be a little bit trickier. So here we have an array, and it can be sorted. It is sorted, but it can be rotated. So you can see, like, I have 1, 2, 3, 4, 5, but I might rotate it where I might take these numbers and put them up here. So there's going to be either no rotation or a rotation. So let's just check for the no rotation first, and you can do this a bunch of different ways. So if an array is completely sorted and there's no rotation, like, you can see that, like, the minimum will be smaller than the maximum, and if it's rotated, then the minimum will be bigger than the maximum because it'll be rotated. So we can just say if num0 is less than or equal to num's -1, return, what do they want, the index, minimum element, num0. So now we know that the array is rotated for sure. So then what do we need to look for? Like, how do we actually find it? And there's a bunch of ways to do it, but essentially you can see that when an array is rotated, the left half is actually bigger. Like, every number in here is bigger than here. So we can just compare what number we have to num0, and then if it's bigger or equal to num0, then we know it's on the non-rotated section. So we can write some pseudocode here. So just pick a random value. And then if it's, first of all, how do we know right away if it's rotated? So we know it's rotated because it'll be smaller than the one before it, right? Like, if you see this, all these rotated ones, the minimum is actually the only number that's smaller because it's always increasing and then it, like, drops. So if it's greater or smaller than previous number, that's the result. So that's one thing we can do. The other case is, and we can just return. So then we just have two cases. So number is greater than or equal to left value in the array. And there's a bunch of ways you can do this, but essentially this is one way. Then we know we're on this, like, bigger side. So if we're on this bigger side, like, if we just check the left value, and if the number is bigger or equal to, then we know we're on this, like, non-rotated section. So then we have to go right. And then else go left, because then we're on the smaller side, but we're not on the minimum number. So then we have to go left. Now, some things to look out for binary search. So when you're comparing numbers to neighbors, you have to make sure you set your left and your right correctly so you don't go out of bounds. So for example, if I'm comparing something to the number to my left, I can't have it be the 0th number. But luckily, if it's rotated, our result can't be the 0th number, because in order for the min to be the 0th number, it would have to be sorted. So we don't have to worry about that. So now instead of setting the left and the right to 0 and nums length nums minus 1, we would just set it to 1. So then we can never be like out of bounds. Okay, now we can just do our check. So we have our hit, we have our go left and then go right. We don't need to record anything because we're guaranteed to find something here. So okay, so same thing, pivot. And yeah, the main thing is I would recommend, so they show these templates where you do this or you do this and then you return left or right. I would always stick to this and just make sure the numbers, whenever you're comparing to neighbors, just make sure you can do some comparisons ahead of time like this, so you never have like out of bounds errors. Okay, so that. So if nums pivot is less than nums pivot minus 1, then this is our minimum, so we can just return it. Okay, if nums pivot is greater than, I mean, it has to be strictly greater because I think all of these are unique. Yeah. So, but we could do greater than equal to, yeah, basically if nums pivot is greater than this, that means it's on the left side, so we have to go right. So nums 0. We have to go right, so right is going to be this way. Oops, this way. And it's always left is pivot plus 1 and right is pivot minus 1 in all of these. You just have to figure out which one goes where. It'll never be like left is pivot minus 1 or something. So, and yeah, that should just do it, I think. Okay, next. Okay, so this one, so we're shipping packages. The ith package has a weight. Each day we ship packages. We may not load more than the weight on the ship. Return the least weight capacity of the ship that will result. So this is what I was saying, kind of that same example where we're trying to find the least weight that will work. And this is where we can binary search on the weight itself, because if a weight of like 10 will work, then we know that like basically, let's see, turn the least weight and read one more time. So okay, so we can't load more than the maximum weight capacity on the ship. Yeah, so we know if like 10 works, then we know or actually, let's see. So if we know a weight of 10 works, let's read it one more time. Okay, so these are the weights. Let's just actually look at the example real quick. Okay, so capacity 15. Oh right, so the weight is the weight of the. Yeah. So it's actually not the weight. We're looking for ship capacity. Yeah. So we're looking for ship capacity. So if ship capacity is 15, it can have a maximum weight of 15. Okay. So we know that like if a ship capacity 15, like for 15, these things can fit on every ship, right? Because this is 13, this is 15, I think. Yeah. We know that like a bigger ship capacity will work as well, right? Because a bigger ship capacity will also be able to hold all of these as well. So we know for sure, so we can write this down, like if capacity X lets you ship in, not ship, in some days, then X plus 1 or greater will also work. But we're asked for the minimum, so we don't really care about any of that, right? But yeah, and then if capacity X fails to ship in some days, then we know the opposite, X minus 1, will also not work, right? So for example, if capacity of 10 is too small, then, you know, anything smaller won't work either. So by doing this, we can just check like, okay, for a given capacity, which does it succeed or does it not? And if it succeeds, then we'll try smaller. And if it fails, then we'll try bigger. And it's the same kind of thing. So we can actually binary search on the answer we're looking for. And so this is like the less obvious where it's not a sorted array, but this is a pretty common pattern as well, something to look out for. So when you're asked for like this, you know, least result where something can happen, ask yourself like, if I know that X can happen, can X minus 1 happen? Can X plus 1 happen? If so, I can actually just binary search on that. So what does that typically look like? So it's pretty common, or it's like a, not pretty common, but like it's a pattern you can use everywhere. So first you make a function that given a guess, is it possible? And then you use that function in your binary search. So we're gonna make a function given a guess of like capacity. And then we want to figure out, okay, we have a chip capacity. So then how do we, how do we want to put packages on the ship to basically, and you want to be able to do this quickly, right? Because if this function takes forever, then it kind of defeats the purpose. So how do we put packages on the ship where, no, they also tell you it's in order. So like I can't put like 1 and then 10. So I have to put these on in order. So what would be like the best way to put it on in order? Well, it's pretty simple. We can just put them on the ship until we exceed the weight. And then once we exceed the weight, we'll add a new one. And then we'll just check like how many days does that take, right? So that's what we're gonna do. So we're gonna say result equals 0 for W in weights. We'll have like a total or like a chip total or whatever. And then we'll say if total plus W exceeds the capacity, which is our guess, then we'll have to make a new ship. And there is an edge case here where if your capacity is too small, you'll never be able to ship it. So we'll just initialize our bounds for that, right? Like for example, here if we pick a ship capacity of like 5, anything bigger than 5 will just never get shipped. So we can just initialize the smallest value we try for capacity as the max of the weights. That's the other thing. For these kinds of problems, you want to think like what makes sense to pick these things. Yeah. So if this is the case, then we're going to basically add a new day. So we're going to say result plus equals, actually we can set it equal to 1 here. And then that, because we need 1 day for sure. So result plus equals 1 and total equals W. Otherwise, we'll just keep adding. And we're just going to check. So the result is how many days it took to ship. So this has to be less than or equal to days. That's the other thing. If it took less than the days, then we succeeded. So now we have this function that like given a capacity, it'll tell us yes or no. And then we can just binary search off of that. So what are we trying to search for? We're trying to search for, let's write this here, trying to search for the biggest weight, not the biggest, the smallest weight or capacity that we get a true for in the check. So you can think of smallest or leftmost capacity, right? Leftmost. So whenever we try a result, we're gonna do that. So this is when I would record result, because we're not just looking for an exact value here. So first let's figure out the bounds. So like I said, what's the smallest capacity that this will ever work for? That will just be the maximum of the weights, right? So maximum of weights. Now, how do we ensure that we pick a capacity that it always works for? By the way, binary search is pretty fast, so you can't just pick like some super big number if you're not sure. Like you can just pick like 10 and 9th and it'll be fine. And for left, you can pick like 0, but then you have to make sure that here, if you ever get a weight that's bigger than your capacity, then you would just return false. So you have to handle that. But yeah, the smarter thing is basically, well, we can ship everything in 1 day if we just make the capacity the total of the weights. So we can just do sum weights here. And now we do the binary search. And also, so what do I want to initialize my result to? Well, we can initialize the result to right. Because we know for sure that like if we just make the capacity, all of this combined, we know that'll always work in time. So then we're going to use the template. So always this pivot equals left plus right on 2. So we're going to say if check guess. So if this returned true, this might be the result, but we're not sure. So we're going to say result equals pivot. And then we need to try smaller capacities. So that means we need to go left. Otherwise, if this capacity was too small, we need to try bigger capacities. And then see how simple this is? Like you can never go out of bounds. You don't need to know, like, do I return left or right or whatever that some other templates do. This is very simple. We just initialize our result, we update our result, and then all we do is just whatever our best, we just return that. And that's it. And I misspelled some stuff. God, this needs to be P. And got a wrong answer. Perfect. Okay, let's see. So output 10, 15. Okay, so if total plus W is greater than guess. Okay, there we go. So hopefully this one makes sense. This one's a little bit unintuitive when you first see it. Like, oh, I can actually binary search on things that aren't disordered array. But now that you have, you can like use this for other problems. So this one's very similar. So you have n piles of bananas where the ith pile has I bananas. and you can eat per hour speed of k. Every hour you can choose a pile and eat k bananas from that pile. If the pile has less than k, she eats all of them. She eats slowly but wants to finish eating the bananas. Return the minimum integer k such that she can eat all her bananas. So this is literally the same thing, right? Like this k is telling you how many you can eat, and then what's the minimum where I can complete my task on time. So I know for sure, same kind of thing, right? Like if k is true, then k plus 1 will be true, k plus 2 will be true, k plus 3 will be true, all those will be true. If k is false, then we know that like any slower speed will also be false, right? So k minus 1 equals false, and so on. So what am I looking for here? So we can write it again. So we're looking for the smallest or leftmost k where check returns true again. And so we're going to write this check function again, and we're going to figure out like how this works and how do we need to calculate it now. So let's take a look at some of these examples. So here, so let's reread it as well. So you can eat, k per hour, you choose a pile, you eat k bananas. If the pile has less than k, she eats all of them and will not eat any more. Okay. So here also it doesn't really matter in which order you eat, because let's say you eat 4 per hour. This will take you 3 hours no matter what, and you won't eat any more. This will take you 2 hours, this will take you 2 hours, this will take you 1 hour. It doesn't really matter in what order, right? Like if I do, for example, 3, 6, 7, 11, this will be like 1 hour, 2 hours, 2 hours, 3 hours. So the total here will be 8. And if I just do some other random order, like 7, 6, 11, like I'm never eating from multiple piles, so it doesn't matter. This will also be 2, 2, 3, 1, which will be 8 again. So I can just start eating. Like how do I want to do it? How do I want to figure out like how many hours it takes a pile? So basically it's just going to be the number in the pile divided by whatever your per hour thing is, floor divide. So we can do that. So we can say like total equals 0 for p in piles, total plus equals the pile divided by our guests, right? Yeah. And we just need to check that return total is less than or equal to the number of hours that we have. So we have our guests, so we're gonna do the same thing. And what does it make sense like here? Like what does it make sense to pick the left and the right? Well, here, I mean, you want to at least be eating like 1 banana, I guess. Like if it's 1, it's possible. Maybe you can pick something better. But like I said, for binary search, as long as you pick stuff where your answer is in between them, it doesn't really matter. Like if I pick 1 or the max of piles or whatever, it's super fast anyway, because it's log n. Like log of a million is like a small number, so it doesn't really matter. So if you start with 10 or 20, that literally doesn't matter at all. So we just need something that works. So yeah, let's just say that the smallest we can eat is like 1 banana per hour. With 0, we'll just never finish. And then what does it make sense to pick for the biggest? So no matter what, we can only eat 1 pile like at a time. So the biggest just makes sense to eat like the max of piles in an hour, because that way we can eat every pile in an hour, and we can't do any better than that. Yeah. So the hours has to be greater or equal to pile's length, because otherwise you'd have no solution. So we'll just say the fastest we're ever going to want to do it is max of piles. Anything faster doesn't give us anything better, because we'll eat every pile in an hour. Now we're going to have a result. What does it make sense to set it to? Well, we can just set it to the right because we're trying to minimize. But you can also set it to like none or whatever. It's fine. Okay. So pivot. So if check of our pivot, that's our guess. So if this is possible, we're going to record it as our result. And we're going to try smaller numbers because we're asked to get the minimum. So this way. Pivot minus 1. And if this is too slow, then we'll go the other way. And once again, return result. See, honestly, if you practice this enough, like you see, like when I run into problems like this, once I recognize, oh, this is binary searchable, then I just think, okay, what's a greedy check function I can write to do this quickly? And then just binary search on that, and then it's like super quick. And get everything wrong. Perfect. Is everything off by 1? No. Okay, I just screwed up. Let's see. Return the minimum k. Okay, let's see. So if I pick 3 here, so this will be 1, 2, 3, 4, 5, 6. And then this will be like more, right? Yeah. So what did we do wrong this time? Okay, let's start off by printing check of the guess. Like, let's try 3. Let's see if this gives us true. I guess it should, right? Yeah. Okay, so for some reason it's giving us true. So this is 1, 2, 3. Oh, right. So I did a floor divide, which was a mistake. So like 7 floor divide 3 would be 2, but the problem is we can't do a floor divide. We have to do a ceiling divide because 7 actually takes 3 hours. So if we have a remainder, that takes another hour. So this is just, instead of a floor, we need to do a ceiling. So this will be correct now. Okay, there we go. And yeah, so these are the main binary search concepts. You're going to have problems that like part of it is binary search, but these are the main things to look for. Predictable arrays or results you can binary search over. And then yeah, like I said, I would recommend this template. You can also look into like bisect and other stuff. But yeah, this, I just use this for everything, and then I don't have to worry about what to return, you know, with the bounds and all that other stuff. And I can do these problems very, very quickly and with like almost no mistakes. So yeah, thanks for watching, and hopefully this helps you.